Hello, everybody. I presume we're ready to start now. We're running a couple minutes late, so I'll try to catch us back up. I know it's the last session before lunch, so I'll make sure we get out of here on time or a little bit early. My name is Glenn Tamkin. I'm a software developer with a subcontractor called CSC on a NASA contract. What I'd like to talk to you about today is how we're leveraging Hadoop at NASA to perform some climate analytics services. As far as a little context here, I'm the lead software developer, software architect. We have a very small team. We're doing a year-long project. We're about midway through the project. Prior to that, there was a prototype with a homemade cluster in our HPC environment. And now we've gotten funding to build our own real cluster. Like I said, we're building out the services now. So this is my first time at Hadoop Summit. I was here for the first 2 days of Birds of a Feather sessions and this morning. And I think that our use case, so far, as far as what I've seen, is a lot different than a lot of the other ones I've seen. In that, in a lot of ways, it's simpler. We're looking at a lot of data that's accrete only. It's accrete only and it's read only, so we never have to update it. We're just going to eventually update it over time, or perform operations on it over time. On the other hand, the data itself is a little more complex than some that I've seen, or at least different. It's binary data, so we have to look over fairly large files and be able to perform, in the end, MapReduce operations effectively over big data sets. So just a couple more context slides before I talk about the Hadoop specifics more closely. Just overview-wise, at the NASA Center for Climate Simulation, which is where I work at Greenbelt, Goddard Space Flight Center, we've traditionally been an HPC environment, high-performance computing environment, that focused on giving the end users, which were climate scientists, the ability to actually log on to systems, run their scripts, load their data, process their multi-step experiments, and basically run their own show. We're still going to provide that service, but we're trying to add a layer of data services on top of that, which will allow them to do their job a little bit more effectively. And I won't talk about that in any great detail, but I'll talk about the one related to Hadoop. Here's a lot of acronyms on this slide. The only thing I'll point out there is this particular data type that we're building our services over is called MERRA, which stands for Modern Era Retrospective Analysis for Research and Applications. We're building analytical services on top of that. MERRA is unusual in that it's a combination of observational data and simulation data, and this isn't all that important to everybody here, but it's a little bit relevant as to why we're using it. That means that we have points in time, basically over the last 30 years since 1979, where we have observational information that's been collected from various sources, typically satellites. In between those data points, we're using models to basically fill in the gaps. What's interesting about that? Well, it's that we can define what we're interested in, including in the models, and how we actually tune and optimize the outputs to perform, or at least provide different kind of climate-related services to the community. MERRA, like I said, it's about 30 years. It's been collected for about 30 years, and it's continuing on. But what we want to do is provide a one-stop service over that data set that allows climate scientists to do reanalysis experiments. And the other unique thing about this type of data is it's got a certain number of variables within it that is rarely seen in a certain data set. When I say variables, I'm talking about things like temperature, surface pressure, wind velocity, things like that. The vision is basically to provide a test bed, but a production level test bed where we can provide services that will allow users to do queries across this time span I mentioned. The queries will typically be including a time span, a geospatial extent, like a lat-long bounding box, perhaps a certain level or surface level of the Z above the Earth, and obviously whatever variables they're particularly interested in. We want to provide sort of multiple use sets. One that serves the original use cases of our climate scientists that log on to a shell and actually want to do work. We're also going to roll that up into a web service layer on top, RESTful web service layer on top. Ultimately, we want to provide an approach that can be used for MERRA, but we can use for other data types One of the things we're doing here that might be slightly different, and it's a little bit, I think, slightly risky from some other things we've used, is we want the scientists to be able to actually build their own jobs if they want to. We'll see how this really works out, but the point is they'll be able to ingest their MapReduce jars and be able to run them through our API. And we'll be able to kind of organize through workflow approach their artifacts and be able to provide them back to the user. Okay, just one more background slide here. I mentioned we're halfway through a year-long project. Prior to that, we did a quick prototype. Since we're an HPC environment, we have a lot of hardware. We were able to kind of cobble together locally a cluster, and we did some very basic operations using MapReduce in a very small subset of the MERRA data. We had enough success that we went to headquarters and convinced them to have, let us fund the entire project. I say that because this is somewhat retroactive to what we did before we fully started things. But some of the benefits were we used HDFS for the parallel distribution of data such that we could bring the computation to the nodes, classic Hadoop and MapReduce benefits. We focused on a very small set of operations at the beginning, and we captured some metrics and performance improvements as we tweaked some things. I'll come back to that. I'm going to admit straight up, our focus, and perhaps wrongly, has been focused less on performance and more on providing functionality. We kind of consciously decided we're going to try to tune in performance later. I don't know if that'll work, but that's kind of our strategy right now. Okay, I think I mentioned that the reason we wanted to go Hadoop and MapReduce was to use the parallel storage. We're using a workflow generator approach to perform analysis over the MERRA data. So I mentioned our vision is to have these canonical operations eventually, things like determining an average over time, the minimum value over time, max, count, variance, standard deviation, things like that. Just basic canonical operations. But we want ultimately to let the user to be able to script out a full complex chaining of events. May look at Uzi for that, I'm not sure yet. And finally, we're introducing an API that exposes the climate data services. I already mentioned the web service API. We're also building a Python client on top that will be able to invoke the web services and ultimately do Python, conditional logic there. So we're hoping we're going to give our scientists the most flexibility they need through a pretty basic and simple set of primitives. Okay. And this is the generic why HDFS and MapReduce, and I don't need to tell anybody about this, but what in this room about these details, I'm sure you know, but what was attractive to us as wanting to focus on doing the science was not to worry about fault tolerance, load balancing, failed nodes. We all know there's going to be plenty of failures in your cluster, and you just have to plan ahead for it. Luckily, Hadoop can help us do that in an automated fashion. We co-located the stored data with computational nodes to be able to, like I said before, bring the computation to the actual data. The last bullet there, MapReduce job takes the requested operation and maps it into appropriate nodes for computation using keys, specified keys. Keys, in our case, I think are going to be a differentiator from how we're using MapReduce with a lot of others. And now I'll start talking about some of the details there. Okay, the initial use case, I probably should have shown this earlier, but the initial use case for us getting basically approval from headquarters was this. We're creating a time-based average over monthly means for specific variables. This example is average temperature for the winter of 2000. One thing I should mention, what we want to do is provide these canonical research operations over MERRA, but what the climate industry really would like to be able to do more effectively is to be able to compare outputs across models. We're focusing on one in the case of MERRA, but there are others, other data sources, European data sources, NOAA, NCCS, many others that we would like to be able to compare, that the scientists would like to be able to compare results to help tune their models. That's one of the things we're focusing on here, is trying to provide a mechanism to do that. This is just a slide to summarize some MERRA data statistics. The only things I would pull out of this is that it's a roughly 30-year and growing span. The total size is about 80 terabytes. We typically have files that range from 20 meg to 1.5 gig each, and the difference in the file sizes are there's 4 different types of data. Monthly means, I think I mentioned before, is what you might guess. It's one file that has the mean value for a specific time in a month. Then we have daily files, which would be similar, but it's for a day, and then 3-hour files and 6-hour files and 3-hour files. So the granularity of all those files grows, so does the size, but it allows you to do different experiments and get different results back. So that accounts for the range and sizes. So at our map and reduce level, we have to be smart enough to figure out what files we're looking at dynamically, or use some metadata so that we know how to process that effectively. Classic MapReduce workflow. Apologize, it's hard to read the text on here, but basically over on the left you have a representative, looks like a set of files there. That's our raw MERRA data files. What we do is we ingest those into HDFS. I'll talk more about the details on that. Once they're ingested into HDFS, we submit our MapReduce job, which knows how to filter out the appropriate data based on the parameters that are sent in with the query, and ultimately sends those key value pairs down to the reducers, which performs whatever operation they're interested in. I don't think there's anything unique about this except for perhaps the way that we're sequencing the files is a little bit different. Our MERRA data is binary data. So in order for us to be able, for MapReduce to be able to deal with that or understand binary data, is we have to build our own custom readers and writers. What that translates to is we have to figure out what should be the format of the data when we put it into HDFS. We had at least 3 obvious options. One, we could take each file and just put it in HDFS and give the responsibility for dealing with parsing the data to the application at runtime. One, we could split the file into, keep a file into a logical collection, but take out all the records individually of that and basically provide indexes into those records. That would keep the metadata of the file together in one logical place. And thirdly, we could just split out the records widely across the HDFS and have them be all independent but searchable according to what we're interested in. We chose item 2 because we wanted to keep the metadata together, and so far it's proven to be a good choice because before we kick off the MapReduce, we go through, MERRA is a series of, I think it said 25 different collections, but they all share time and variables. So we actually have to go through and figure out what files we would even want to send to the mapper first. The metadata that we kept in the HDFS helps us to do that quickly because luckily in the case of MERRA data, which is NetCDF data, the time span of the file is in the file name. So we can kind of quickly filter out stuff that we're not interested in. Sequence file format. Okay. The thing that we really agonized about many times, and we've had discussions about it over the last year and a half, is what should be our key? And we've always arrived back at the same general design, luckily. So over there on the left, we basically have 3 logical records, and if you can see it up closely, it's got a composite key and a value. The composite key has a timestamp and whatever variable the user might be interested in, or whatever variable is in the file. So basically that combination is going to allow us at runtime to be able to at least filter out the initial set of data based on what the user wants to see and what the time span is. Ultimately, through the map and the sort, we get a merge result, which then gets reduced, and we calculate whatever canonical operation there is. It's not rocket science, the methodology we're trying to do here, but the trick is getting the data into HDFS in the proper format, being able to read it back out, and being able to do that in a timely fashion. Like I said, if we get, we're still uncovering use cases because we're fairly new in this, and my worry is that we're going to uncover a use case which is going to make us have to, resequence the 80 terabytes of data again. Maybe that's not a big deal, or maybe that's just what we have to plan into the process. But It takes a lot of time to do that and resources, so I'm hopeful that we have the right design here. Although we are uncovering some use cases already that makes us want to consider adding some other metadata there, but we may do that externally. And this is just a couple more metrics on the representative data sets. The only thing that's really important here, these are monthly means files, again, the types we did the initial prototyping on. It shows the raw space there. And in one case, the top one, which has NPANA in the name, that's a higher resolution data set than the other. We purposely did two different ones just to see the kind of results we would get. And as you might guess, the sizes are bigger. For the NPAN, it's got 84 raw gigabytes, which gets sequenced out to 224. It takes 30 seconds to sequence it. This is just anecdotal stuff, but kind of interesting to see as we go along. And we're going to be comparing that with the more granular files as well, with the 6 hour and the 3 hours, which we haven't ingested yet. Okay, this slide compares the results after we got rid of our Frankenstein cluster. We got a real cluster. That's not important to anybody here. That we had to speed up roughly in every category. That's good. We hope that. So what we have here is the same two data collections. The rows in each are 1 year, a 10-year, 20-year span, and then all 30. I guess the important thing here, or interesting thing, is the average processing time per year decreased as we added more years. Very slightly, but it did decrease. So as we know, if we did 1 year, which I'm looking at the top row and the top one there, 1 year is 32.4 seconds. The average for that, for the rest of those, were around the 12-second range. So you can see there's a lot of initial processing just to get the first year going, as with every MapReduce job. Again, I'm the software guy, so I'm not going to go into any detail on this, but it's just a representative picture of our cluster. In our case, we have 34 nodes. It doesn't compare with a lot of the other use cases I've seen here, but it's sufficient for what we're trying to do, at least now. MERRA data up top is 180 terabytes. That's a misprint. That should be 80. And I'm not going to go into detail here either. We're using Intel Sandy Bridge processors on Dell R720 nodes. Okay, I'll touch on the open source tools that we're using. We're using, once we went from prototype to, I would say, production use, we chose Cloudera to help us, mostly because, and this isn't specific to Cloudera, other, like Hortonworks does this as well, allows you to install, monitor, configure your system pretty easily. So from the sysadmin and the actual cluster layer, we got a lot of bang out of the buck for using that. You know, Cloudera also gives you a dashboard that shows all the tools you're currently using and how they're configured. It's very helpful. From the development standpoint, I mean, I develop with Cloudera Manager, but I use it for job monitoring, things like that. But we honestly, and this is getting back to a point that I mentioned earlier, wrongly or rightly, we're not focusing on trying to speed up the application or speed up the cluster or the whole framework right now. That's what we're going to do in the last quarter of the year. And I hope we're effective with it, but you know, time will tell. The point of that is we haven't taken advantage of all the Cloudera or management tool kind of optimizations. This is just a toss-in slide that shows the different, I guess, clients that we have in mind or currently have for this MERRA service. I won't go into detail. There's several. The summary is there's some other government agencies. There's some vendors. There's some private organizations that want to use the data. Okay. So the next steps for us, and I'm about to show the conclusion slide, is we want to, like I said, tune the MapReduce framework, review our application, see if there's what we can do there. we really should get our head out of the sand and look at the other tools in the ecosystem that could help us out with what we're doing. We haven't done that so much yet. Want to complete the application development through the canonical operations, and ultimately we want to consider different ways to sequence the files, but like I said, we don't have a hard use case for that yet. May want to experiment with some data accelerators, but I'm not sure about that. All right, this is the last slide here. So, conclusions and lesson learned from our standpoint. Remember, we're newbies, so probably a lot of this is old hat to the veteran Hadoop person, but I wanted to at least capture what we've learned. The design of the sequence format is critical, in particular for big binary data, and I mentioned the reasons for that before. If you have the wrong design, you won't be able to serve the right use case, but also you'll be at risk of having to resequence all your data, which means changing your application, regression testing, all the things associated with that. Configuration is key. Even though we haven't done a lot of optimizing via Cloudera, we have already noticed that if you make a couple changes, you can get drastically different results, sometimes not in a positive fashion. So I encourage you that if you're trying to optimize your environment, change one variable at a time and then retest. And be very organized along that manner. There's so many things you can tweak in the Hadoop world. You have to be careful. Big data is hard. This is obvious, and it takes a long time. I mean, there's no magic. When you're walking directory structures and you're looking at many files and you're doing operations on them, you have to plan the time to get that done. And I would suggest planning time to make mistakes and redo that work. Expect things to fail a lot, especially with huge clusters. You know your nodes are going to fail, but in any cluster you need to have a plan for catching back up. And we're leveraging the fault tolerance and load balancing in Hadoop for that. Hadoop craves bandwidth. No matter what, there's a lot of shuffling and sorting and copying and merging that takes up bandwidth. Generally, I've already heard of several things going on here already at the conference that might help with that, but you need to plan for bandwidth with Hadoop. HDFS, I would say Hadoop installs easy, but optimizing is less so, and that's related to what I said about the parameters. There's so many things you can change. It's almost daunting in a way. And finally, this is just a subjective thing. It's not as fast as we thought for our initial results. I don't know what that really means. Because we didn't have any performance requirements. There's not a service we can compare this to. It's just gut feel is, okay, it takes us like 120 seconds to calculate. I'm just going to pull one out of my head that I know I ran recently. I ran 30 years of data, the whole span, pulled out one variable, temperature, over 1 month, and it took 120 seconds. To me, it seemed okay, but depends on, the client would like it to be faster. So I don't know what to say about that other than we have to review and see if there's other ways we can optimize, or maybe there's things we don't understand yet. It's all still cutting edge to a certain extent. I mean, as you can see, the environment just keeps expanding. It's hard to stay robust, and that's why we're definitely like the mainstream low-end adopters versus the cutting-edge, pushing-edge folks, just because you want to have a stable environment. I know there's trade-offs that way. We're going to not be able to take advantage of features and perhaps not be able to get performance gains that we might otherwise. But we haven't used any of basically we haven't integrated any, what I would say is non-generic Hadoop-isms into our application or our framework or process yet. On purpose, in case we want to move to something else. And finally, take advantage of your support provider, especially for us, perhaps not the leading edge folks, but everything we've done has been done before, and what we found out pretty quickly is even the most absurd abstract messages you can probably find on the mailing list or just via Google. So don't be shy, ask for help quickly, fail fast. So that's basically all I had to say about it. So again, it's a small project at NASA, but if it's successful, we envision follow-on projects to do similar things in the future. Thanks for coming. If there's any questions, I'd be glad to try to answer them. Yes? Thank you. Right. Right. The question is, we started with NetCDF and we potentially did output in a text format, and how do we relate the keys to that? Let me clarify what I really mean here. Is through our full MapReduce process, we start with NetCDF files, we create sequence files in HDFS, we perform MapReduce on HDFS, and create a new single sequence file that represents the aggregate of all the filtering across those sequence files. Then, as part of our process, which isn't Hadoop at all, we convert that back into NetCDF. So there isn't any, we never have any text-based anything. Never did, no. Which is part of our challenge. But.
So if I understand your workflow, all right, so if I understand your workflow, you have a big repository of data, and based on the analysis the user wants to do, you're sucking a subset of that data into HDFS and doing this analysis. Are you counting the cost of that ingest when you're calculating, how fast this stuff goes? Because ingest seems to be a big
right.
problem.
That's a real good point. I should have clarified, we're not dynamically doing any ingest. We were lucky enough to have the entire collection available, and we've just been ingesting that over time as the whole thing. So there's no dynamic ingest, but that's a very good point. Of course, we are going to have to deal with additional data that gets added to the MERRA data set and how we expand out without the services getting disrupted, but there's no dynamic ingest.
So are you dealing with, so that's the part I'm not clear about. Are you dealing with incremental data? So, like it's the end of the day, you collect data because you're trying to do an average or a summary of this data. How do you manage that?
Right. Question is well, I guess everybody can hear the question now. We have a simple use case. We started with 30 years of data that exists. Now, at some point in the future, there will be another year of data that's published, and we will add that in. But we don't have any dynamic addition of data in our case. These are just well documented points in time where data is published that we're just going to add to our HDFS collection. Now, of course, that means we're going to create services that can leverage the new data, and we might have to change things if the new data means providing different services, but we don't really envision that now. It's just the time span will be increased. Thanks.
Hi, so my question is so when you decided to, for a particular block size, so what are the different parameters you took into consideration, and how you reached to that particular number?
Right, a very good question. How do we determine our block size? I didn't talk about that much. We did prototyping with classic block sizes with the initial project, 64, 128, 640, and higher even, 640 megabytes. We found out pretty quickly that if we did 640, it helped us out. Well, that's convenient because 640 is larger than the largest file we ever see. So logically, all our files are very closely located together, even when they're in HDFS. You know what I'm saying? So the block size is large enough that it really gave us performance gains. And in our case, we're not getting any penalty by doing it like that. We have plenty of space to cover that. So we cheated. We just picked the largest block size, and basically got performance gains off of that.
Yeah, and I mean, the following up question. So depending upon that, did you change any MapReduce parameters like slots? Maximum map job or task job MapReduce can handle?
Very good question. The answer is no, but we've identified those areas as what we have to look at closer. I appreciate that. Yeah. Yeah. Good question. The question is, are we seeing patterns in the user queries that can be cached? Yes, and that's been our kind of initial plan, because we know enough about the industry or the climate science groups that we're focusing on based on that slide that there's a lot of common queries they're going to do. I'm interested in North America. I want to see temperature versus surface pressure. But it's the same time frame, what happened in 72 to 79. So our plan is to cache that. And we're designing that in now. We're considering not caching it in HDFS proper and using Hadoop, but a whole separate system called IRODs, which we're going to use to basically capture the workflow artifacts and be able to produce that if we get the same query again. So we're planning for that, but the amount of usage we have so far hasn't warranted. We haven't had enough to cache, but we figure there will be. Yes. Yes, they're able to select subsets. It's very constrained what they can do. There's only 3 possible parameters they can do. But time is one. It's the physical bounding box and the XYZ level, the volume that they're interested in. So we do dynamically create that subset during the MapReduce process. But a lot of that is filtering the data from time, and then we go into. Is that the question you were asking? Okay.
So do you expose that kind of thing in the API?
Yeah.
With the REST API, or is it
The API is basically an order and a series of parameters that are exactly what I just said, the min, lat, lon, the variable of interest. The idea is that we're going to provide a number of services. Right now we just provide one service with a lot of parameters, but we're building in, we certainly know we're going to have to provide different services with different parameters. But right now we're doing the superset of most of the things we can see that are going to be done with MERRA and how they would be constrained. The data in general is public. I mean, you could go download it yourself. The API, the web service will be public. It's not now, we're doing beta testing, but everything we're doing is going to be open to anybody who's interested in it.
how do you do testing? How do you compare the results to, say, XPC, traditional analysis?
Do you have any advice?
Or debugging, yeah.
Right. We don't have, we have 1.2 developers, and I'm one. So we're relying on basically our own testing. We don't have a good regression test set up for results yet. But to answer your question slightly differently, we do take the results of ours and compare them to independent systems. There's another system in NASA called GRADS, which does a similar kind of subsetting over the similar types of data. So we can compare to see if our results are good or not. But we don't have any good automated way to test a number of variations on the different queries yet. Thank you. If there's nothing else, appreciate it. Thanks. Oh. Thanks.